In the last lesson, we talked about enthalpy. This lesson, we will talk about molar enthalpy. And molar enthalpy is a very useful concept. One situation where we would consider molar enthalpy would be if we're trying to decide between different fuels. So fuels can be used to do combustion reactions, right? I can burn gasoline, I can burn propane, I can burn diesel, natural gas, wood, coal. There are lots of considerations when I'm deciding which of these is the best fuel for a certain situation. I would consider cost, I might consider weight, I might consider availability. I might also consider how much energy is released for every mole of fuel that I burn. Because if one of them releases a lot more energy per mole, well, then it's a more energy dense fuel, and that could be useful in certain situations. So to figure out how much energy is released per mole of something that reacts, like a fuel burning in a combustion reaction, I need to be able to calculate molar enthalpy. This is the formula that's going to help me. So if I want to find the enthalpy change, and remember that's measured in energy units. In this case, we're going to use kilojoules typically for enthalpy changes coming out of this formula. And this is my molar enthalpy, or my molar enthalpy change. Now this is the amount of energy released per mole, so the unit is going to be kilojoules per mole. And in order to make this formula work, well, if I have an enthalpy per mole that's equal to enthalpy change, we have to multiply it by the chemical amount. So we have to multiply by N, which remember stands for chemical amount, which is just our fancy way of representing moles, the amount. That's how we count amounts in chemistry, right? We like to measure things in units of moles. And so to kind of get us started with this, I'm going to give you a few molar enthalpies. So here's a table of molar enthalpies of combustion for some alkanes. Now you have to notice a couple of things. You got to really pay attention to the fact that these are molar enthalpies of combustion. So this is the amount of energy that's released. In all of these cases, it's released because the molar enthalpies here are negative. So these are all exothermic, which makes sense if I'm burning something. These are all molar enthalpies of combustion. So for methane, the first one on my list, when I burn CH4, according to this combustion reaction, CH4 methane plus oxygen, gas, gives me carbon dioxide and water vapor. Carbon dioxide is a gas too. And my coefficients here are 1, 1, 2, and 2. So this molar enthalpy is the molar enthalpy for this reaction. Every time 1 mole of methane is burned here, this is the amount of energy that's released. Now, the reason why I'm making such a big deal about that is we're going to consider lots of different types of chemical reactions. We might consider the formation of enthalpy. We might consider the formation of methane. So the formation of methane would look like this. It's a totally different reaction, and it would have a different enthalpy, right? This enthalpy does not represent this reaction because it's not a formation enthalpy. We could have a separate table of formation enthalpy values. And in fact, you do in your data booklet. So you see here a table of standard molar enthalpies of formation. So for all of these chemicals here, these would be molar enthalpies for their formation, according to their formation reaction, like you would have predicted in chemistry in grade 10 science. But for now, let's try an example here using a combustion reaction. So what's the change in enthalpy due to the combustion of 10 grams of propane used in a camp stove? Okay, so I've got a little camping stove. It runs on propane. I'm going to combust 10 grams of propane. So all of those things are going to be important. So I'm doing combustion, so that means that this molar enthalpy of combustion table will be of use to me. I'm burning a mass of 10 grams of propane. Okay, so I have propane here on my table. It's got a molar enthalpy of combustion of negative 2043.9 kilojoules per mole. So let's see how we can solve this here. If I want to know the enthalpy change, that means I want to know my delta H. I know my molar enthalpy. I can look that up on my table, my molar enthalpy of combustion. And just be careful here because this is asking for a chemical amount in moles. And I'm being given a mass. So I can't plug my 10 grams in here directly. I first have to figure out what this would be in moles, right? I have to convert these 10 grams into moles using my molar mass formula. So that's step one. Let's do that first. I need to figure out what my number of moles is. So I've got 10 grams divided by my molar mass for propane, which is 16.05 grams per mole. So we can take 10 divided by 16.05, and that gives me 0.62 ... moles. So there's my N value. And I've got a bunch more change in my calculator, right? It tells me 0.6230529.595, but I'm going to store those digits in my calculator, and I'm not going to write them all down. So then step two, I want to figure out what my change in enthalpy is. So now I'm going to use my new formula. I want to find my change in enthalpy. That will be equal to my molar enthalpy of combustion times my number of moles. So my molar enthalpy of combustion, I can look up here. Here's propane. Keep the sign in here. The sign's important. Negative 2043.9. And the units are important too. Kilojoules per mole. Times my N value, 0.62 moles. So on my calculator then, I'm going to recall that answer, 0.62 ... times negative 2043.9. And that gives me an enthalpy change, a delta H, of negative 1,273. Now the units here, because I've got kilojoules, then I've got moles divided by moles, so the mole unit is going to cancel, and I'm going to be left here with units of kilojoules. I also only get 3 sig digs, so I'm going to have to round this guy. So we could either put this into megajoules, but I might just use scientific notation. So 1, 2, 3, negative 1.27 times 10 to the power of 3 kilojoules. So that's going to be the enthalpy change for this propane as I burn this much propane. And you'd expect that would be greater if I burned more propane, right? Or it'd be less if I burned less. So the mass here is significant, and I took that into account. Let's try another one here. Predict the enthalpy change when 200 grams of ammonia is formed from its elements. So I'm not going to look back up at that enthalpy of combustion table because this is a formation reaction. So I can go to my data booklet. Let's find ammonia. Ammonia is negative 45.9 kilojoules per mole. So let's write that down. Negative 45.9 kilojoules per mole is its formation enthalpy. Molar enthalpy of formation. I've put in the F because this is a formation reaction, but you could leave it out and just say delta HM. It wouldn't matter either way. The thing that is important is that this is a molar enthalpy. It's kilojoules per mole. So we have to keep it straight from an enthalpy change. Okay, so what's ammonia? NH3. I'm going to need that because I need to know its molar mass. I'm being given a mass again, and if I want to figure out the enthalpy change, the delta H, I'm going to need to know N. So mass is equal to, N is equal to M divided by big M, my mass divided by my molar mass. So I'm burning 200 grams of ammonia, and its molar mass is 17.04 grams per mole. So 200 divided by 17.04 gives me 11.7 ... moles of ammonia. And now I want to find the enthalpy change. So I've looked up my molar enthalpy already. So my delta H is equal to my molar enthalpy times my number of moles. The molar enthalpy was negative 45.9 kilojoules per mole. And my number of moles we just calculated, 11.7, with all that change that's in my calculator. So the enthalpy change then is negative 537 kilojoules. So this is another exothermic reaction, which I can tell because it's got a negative enthalpy. Then I don't think I'll do this one because it's very similar to the first one, right? What quantity of energy is released when 450 grams of octane is burned in a sweet Mazda Protege? Oh, that's a dynamite car there. Person would be lucky to have a Mazda Protege. Let me tell you about that. But the only thing that you need to pay attention to here is it's asking for quantity of energy. What quantity of energy is released? So if we had phrased it the same way for this first question, the enthalpy change was negative 1,273 kilojoules. If we had asked what quantity of energy was released, we released 1,273 kilojoules. We didn't release a negative quantity, right? The negative sign is telling us it was released. So for this one here, you can go through the steps just like you did in the first one. And then for your answer is going to be positive, right? Because of the way that it's phrased. So if it asks for a quantity of energy, you would always express that as a positive value.